Welcome back, learners. We are still on the topic on thin lenses. We started it off last time and we learned so many things about thin lenses, their materials, where they come from, why they are grouped into two different types, converging and diverging. I gave you a question last time. Why do we call them thin lenses? Why not operate on thick lenses? Now, if I was to have two types, let me have a thin one and a thick lens, a very thick one. We compare their diameter, D is the same, but I want one to have a bigger curvature than the other. So these are small, let me call it S for small, then this is very big curvature. We call it B for big. Therefore, thin lenses are said to be thin lenses have a smaller curvature. They have a smaller curvature as compared to thick lenses. And this brings out an advantage because this causes them to have what we call negligible spherical aberration. Now, if you can remember very well, this problem on spherical aberration, we found it back in Form 2 when we would say that in case the rays from a source are far away from the principal axis of a mirror, then they tend to create another principal focus somewhere separate. And all those principal focuses, together with the original principal focus, they create something which we call acoustic circle. We find it in some basin with some water. If you leave some basin outside with some water and it's sunny, you find what we call acoustic sort of this way inside the bucket, like a shining, some sort of shining light. That all that is caused by what we call spherical aberration. So we won't have such problems with thin lenses, but if the curvature is too big, then we start suffering from what we call spherical aberration. And if you are writing it somewhere, we can define spherical aberration as it's an optical problem that occurs. It is an optical problem that occurs when rays focus at different. It occurs when rays focus at different focal points, and because I had taken you back to that problem in Form 2 about why the mirror can have such an issue, I also want to give you a hint of how you answer that question. Somebody can ask, why do we prefer, this is back in Form 2, why do we prefer to use parabolic mirrors instead of concave mirrors? This is back in Form 2. And the answer was very simple, that this parabolic mirror, since they are thin, they don't suffer from spherical aberration. So some sort of such knowledge is what we are using here, but now in terms of lenses, not mirrors. Now, next we look at, there are some terms we shall be using in this topic, and I would like us to define a few if our time allows us. So let us define some terms, definition of terms that we shall be using in this topic. And these terms are going to be used when we are looking at properties of these lenses. Now, and I want you to compare them with other definitions that we did in Form 2 pertaining parts of a mirror. Now, the first one is the center of curvature, which we shall be giving a letter C or 2F, and mostly we shall be sticking with 2F. Now, this is the center. It is the center of the sphere. It is the center of the sphere of which the surface of the lens is part. Now, since we know that lenses, they come in pairs. For example, when you look at a biconcave, it's made up of one surface on one side, so it has its own sphere, and the other one here. So it's good to indicate that most of the lenses have, and I'm using the word most, have two centers of curvature, like the one I've drawn here. So this side has its own center of curvature, 2F, and this one has its own 2F, but they are the same lengths. Apart from a plano lens, any plano concave, plano convex, which has one center of curvature. So the other thing we also need to learn is, if we are talking of a biconvex, the centers of curvature are now on the other side, and they are said there, these ones. So this is where we are now going to have 2F for this surface, and then 2F for the opposite surface on the other side. So that's the main difference that we have there. Next, we look at another property or another term apart from the center of curvature. Number 2, we have what we call the radius of curvature. And we shall be giving it R. So since the center was the center of the sphere, then I think by definition also the radius, we say that this is the radius. It's the radius of the sphere. It is the radius of the sphere. Then we can proceed and say of which the surface of the lens, was part of. Number 3, so it's this distance here. This one here, that's what we have as the radius R, and they are both equal on the other side, on each side. Now we have number 3, principal axis, and we are going to write this. It is an imaginary line passing through. Passing through the centers of curvature. The two centers of curvature. It is an imaginary line passing through the two centers of curvature, these two here. So if I drew a line in between them, that line is what we are calling the principal axis. Next, we look at number 4, optical center. We give it the letter O, optical center. It is a point on the principal axis, midway. It is a point which is midway on the principal axis, where a ray through this point is undeviated. A ray through the optical center, is undeviated. We say that in case light was to pass through, so in between here, we have what we are calling the optical center. A ray that passes through here is not, for example, in this example, a ray through this point, since this is known as a converging length, it doesn't converge. A ray through this point does not diverge. Even if it was straight, it still moves in a straight manner. Now, there's another one more term, though we are not going to define that for today, since apart from these terms that are shared by the two lenses, The last term, number 5, which we're going to look at next time, is different for this type of a lens and different for this type of a lens. So we stop at that. Let us meet next time. Thank you.